That was intrinsic evaluation. Now let's look at extrinsic evaluation, how you can use clustering to help you do something else. And we're gonna talk about using clustering for image representation. So suppose that your goal is your task is you get a bunch of photographs, and your goal is to detect presence or absence of certain objects in those photographs, or automatically annotate the images. So as a first step, of course, you have to take your images and represent them in some way. So we have to come up with attribute value representation for each image. In this case, you have natural photographs, so taking individual pixels as attributes wouldn't be a very good idea. You have lots and lots of pixels, lots and lots of colors, so you're going to end up with lots of attributes, and each attribute by itself is going to be totally uninformative about whether the image contains a certain object or not. And part of the problem has to do with the fact that representing an entire image, an entire scene, is a very difficult problem. So it's difficult to describe in terms of features a photograph like that has some water, maybe some sky, maybe not, some grass, an animal, ripples in the water. It's difficult to describe an entire image in terms of a single feature vector. Now, what is easier and what is possible is if you took this image and you cut it up into little chunks. So maybe you cut it up on a regular grid, or maybe you did some segmentation. So you break the image into little patches. Right? Now, a single patch is easier to describe than the entire photograph. Why? Because a single patch probably is covered by one object in the image. Right? So that patch right there is grass. So whatever properties grass has should be encoded in that patch. And that patch right there is, the tiger patch. So it'll have a certain color distribution, which is unique to tigers, a certain texture distribution, a certain orientation of edges in that little patch. So describing a little patch is a lot easier than describing an entire image. So we'd like to come up with a representation that works in terms of those little patches. And that's straightforward. We can take a patch and compute some computer vision features based on that, right? So we could compute a color histogram inside a patch, and that would be meaningful. A color histogram over the entire image is not very meaningful. But in a small patch, it can tell you a lot about what that patch looks like. You could look at the texture, you could look at edge orientation, all sorts of other things computed from a small patch. So that's nice. We can represent a single patch as an attribute value vector, and then we'd like to run our classifier. The problem, however, is if we do that, we're going to end up with a bunch of different feature vectors. We're going to have a separate feature vector for every one of those patches in the image. And our clustering, and not just clustering, all of our learning algorithms, they assume that there is one and only one feature vector for the entire instance. So all of the methods that we've described and all of the generic machine learning methods, they always assume that an instance is represented by a single flat feature vector, attribute value vector. And here we got a bunch of them. So what do? Can we concatenate them all end to end to make one big one? Is that a sensible thing? Okay. We had this in the first tutorial, right? It would be a sensible thing if you always expected grass to be in the upper right part of the image. So if that patch was always expected to be grass and this patch was always expected to be tiger, then it would be a sensible representation. You could concatenate all of those vectors. But because grass can be anywhere in the image, you don't want to put it in a particular part of the feature vector. So really what you want exchangeable feature vectors. Feature vectors that can occur anywhere in the image, and they would mean the same exact thing in the image. So one way to achieve that is if we could take this feature vector and represent it with a word or a label, then we would have a bag of words representation, which we know how to do, right? So if someone came along and said that that feature vector corresponds to grass, that would be nice. Okay. The problem is, to do that, we would actually need human beings to assign labels to feature vectors, right? And if they were assigning labels to feature vectors, they might be saying they might as well classify the images for us, so we wouldn't need to bother with that. So you can't do that. But what you can do is you can group together similar feature vectors and assign labels to them. These wouldn't be humanly interpretable labels, but at least they would be consistent. So instead of saying this is grass, which requires human intelligence, we're going to say this is C27. And what we can do is we can use k-means to come up with that description C27. So how do we do that? Take a bunch of, so take your entire data set, all of the images that you have in your data set, extract all the patches from all the images. Every patch is represented by a small feature vector, as on the previous slide. So maybe it's a color histogram, maybe it's edge orientation, maybe a texture histogram or something like that. So every little patch has a vector. Now what I can do is I can cluster the patches. I can run k-means with, say, 500 centroids, and what it will do is it will take all the patches and try to group similar patches into the same clusters. Now these patches will be similar in terms of their attribute value representations, but our attribute value representation reflects visual appearance. Right? A color histogram reflects the colors that you see in a little patch. So what would happen, or at least what you hope will happen, is that all the patches that look similar will kind of end up maybe in the same k-means cluster. So maybe all the patches that have blue in them end up in cluster C79. So that patch of water, it'll be in C79. That patch of sky, it's bluish. That patch of sky, that patch of sky, that patch of water, they'll all go into C79 because their visual appearance is similar. Not because they represent the same object, right? Some of those are water, some of those are sky, but they're all visually similar. Similar color histograms. So they'll maybe all go into C79. Green patches, patches that have large proportions of green and maybe vertical edges, they'll go into C27. And maybe these tigery patches or seafood patches that look kind of like a tiger, maybe they'll go into C14. So what k-means is doing for you, it's taking those vectors and putting them into groups. And what you know is that, by definition, all the vectors in a group, all the vectors in a cluster, will correspond to similarly looking patches. So now what you're going to have is you're going to have a label, a cluster label, for every patch in every image in your data set. And you can use those labels directly for representing the images. So now you're back to one specific image. It had a bunch of different patches. You look at which clusters did those patches land in. So the bluish patches, maybe they land in C79. The greenish, they land in C27. The tigery patches, they land in C14. So what you can do then is you can represent the entire bitmap using a bag of cluster labels. So the representation would look kind of like that. So I have, if C14 is a word, right, this image has 4 occurrences of C14, 1, 2, 3, whatever the 4 are, 7 occurrences of C27, 24 occurrences of C79, and no other cluster labels. So think about what you've done. You've gone from having a bitmap, which has lots and lots of pixels, which are not very informative, to having lots of patches where each patch has a separate vector. And now what you've done is you've replaced that vector with a label. And now you have your bag of labels representation. So you can use all of the algorithms in this course automatically on, so you can try any algorithm to classify images. Right? You've come up with a flat representation. And the way you got that is by using k-means clustering on the individual feature vectors.